sampling distribution which is important and it is used quite frequently is F distribution. So, now I introduce the F distribution here. Let y 1 and y 2 be independently distributed random variables. And y 1 follows say chi-square distribution on m degrees of freedom and y 2 follows say a chi-square distribution on n degrees of freedom. Then if we define a variable called u as the ratio of this y 1 and y 2, but divided by their degrees of freedom, that is y 1 by m divided by y 2 by n, that is basically becoming n by m y 1 by y 2. Then this is said to have an F distribution on m n degrees of freedom. Now, here one has to notice that 2 degrees of freedom terms are coming and therefore, this order is important. If I am having a numerator chi-square variable as m and the denominator chi-square as n, then we will write the ordered pair m n. That means, if I write n m, it will denote a different F distribution. Now, by our theory of transformation of random variables, u is a function of y 1 y 2, therefore, I can use a new dummy variable v and find out the joint density of u and v to derive the probability density function of u. So, for that purpose we write the joint distribution of y 1 and y 2, the joint density of y 1 and y 2 is f of y 1 y 2. So, basically we multiply the individual densities of y 1 and y 2, which are basically chi-square densities on m and n degrees of freedom. So, if we combine the coefficients 1 by 2 to the power m plus n by 2, gamma m by 2, gamma n by 2, e to the power minus y 1 plus y 2 by 2, y 1 to the power m by 2 minus 1, y 2 to the power n by 2 minus 1, where both y 1 and y 2 are positive. So, we consider the transformation in which u is this variable. So, consider the transformation u is equal to n by m y 1 by y 2 and v is equal to say y 2. So, the inverse transformation is y 1 is equal to m by n u v, y 2 is equal to v. So, the Jacobian of the transformation can be calculated as m by n v, m by n v u 0 1, which is basically m by n v, and since the terms are positive. So, absolute value of j will also be the same. So, the joint density of u and v is now you can observe we are having here this constant term and we will be replacing y 1 by m by n u v and y 2 by v. So, here v by 2 term will come out and this will give additional powers of v, for power of u will be this one only. So, after adjustment of the terms we can write it as m by n to the power m by 2 divided by 2 to the power m plus n by 2 gamma m by 2 gamma n by 2 e to the power minus v by 2 1 plus m by n u, u to the power m by 2 minus 1, v to the power m plus n by 2 minus 1, where u and v are positive variables. So, we can integrate with respect to v from 0 to infinity to get the desired density of f random variable. Again, if we observe, the integral of this with respect to u is nothing but a gamma function, where the order is m by 2 and the coefficient is 1 plus half into 1 plus m by n u. So, using the standard argument, the marginal density will turn out to be the marginal density of u is then f u is equal to m by n to the power m by 2, and after the cancellation of the terms we will get it as 1 by beta m by 2 n by 2 u to the power m by 2 minus 1 divided by 1 plus m by n u m plus n by 2 for u positive. Obviously, this is a distribution of a positive valued random variable and it is positively skewed. However, the shape will vary depending upon the values of m and n. So, I can just give one example here. If I consider say m and n is equal to 5, then the form of the density is somewhat like this. If I consider say m is equal to 5 and n is say 15, then the form is something like this. So, likewise for different values of m and n, you get different shapes of the curves. Here calculation of the moments will make use of different beta functions. However, I will write the mean and variance. The mean of this is n by n minus 2. You may be little bit surprised here that it is dependent only upon second variable, because m is not appearing here. Variance of u is equal to, here you need n greater than 2 and variance term is twice n square m plus n minus 2 divided by m into n minus 2 square into n minus 4. This is valid for n greater than 4. This positively skewed distribution. So, we concentrate on the points here. So, if I have this probability equal to alpha, then this point is termed as f alpha m n. That is the probability of u greater than or equal to f alpha m n is equal to alpha. That is, this is upper 100 alpha percent point of f m n distribution. Now, by the definition of this f variable, it is clear that if I have u following f m n, then 1 by u will follow f n m, because 1 by u remains a ratio of chi square variables divided by their degrees of freedom. However, the numerator degrees of freedom have gone to the denominator and the denominator degrees of freedom have gone to the numerator. So, this becomes f distribution on n m degrees of freedom. So, we can derive a formula for the points of f distribution. So, we defined that f alpha m n is the upper 100 alpha percent point of the f distribution on m n degrees of freedom. So, probability of u greater than or equal to this is equal to alpha. So, if I write it as probability of 1 by u less than or equal to 1 by f alpha m n, then this 1 by u is a f n m variable, that is, this is probability of some v less than or equal to f alpha m n, that is, this v is f n m variable. So, if I am saying that v greater than 1 by f alpha m n, this equality or inequality does not play any role here because of this continuous distributions. So, I am saying probability v greater than or equal to 1 by f alpha m n is equal to 1 minus alpha, but V is f n m distribution. This implies that f 1 minus alpha n m is equal to 1 by f alpha m n. This relationship is used for calculation of the percentage points of the f distribution, and generally the tables are, because here it is a 2 dimensional table, you have m and n both varying, and therefore, only for selected values of alpha the tables are given. Now, if they are given for say alpha is equal to 0.05 or alpha is equal to 0.1, then 1 minus alpha becomes 0.95 and 0.9 respectively. So, those tables can be automatically derived from the tables of 0.05 and 0.01 values, etcetera. Now, we look at that how in the sampling it arises. So, if we consider say a random sample say x 1, x 2, x m following normal mu 1 sigma 1 square, and say y 1, y 2, y n be a random sample from normal say mu 2 sigma 2 square. And also I assume that these samples are taken independently. Let us define the quantities, say S x square as m minus 1 by m minus 1 sigma x I minus x bar square I is equal to 1 to m, and say S y square as 1 by n minus 1 sigma y j minus y bar square. Then by the theory of chi square, m minus 1 S x square by sigma 1 square follows chi square distribution on m minus 1 degrees of freedom, and n minus 1 S y square by sigma 2 square follows chi square distribution on n minus 1 degrees of freedom. Let me call it say u variable and this as the v variable. Then if I take the ratio u divided by m minus 1 divided by v divided by n minus 1, then this is nothing but sigma 2 square by sigma 1 square S x square by S y square, that follows f distribution on m minus 1 n minus 1 degrees of freedom. So, this relationship or this result is used quite frequently in drawing inferences on ratios of the variances, because ratios of the population variances and ratios of the sample variances is occurring here. Another relationship which is coming here is that if say t follows t distribution on n degrees of freedom, then t square follows f distribution on 1 and n degrees of freedom. One can prove it by direct transformation by writing down the density of t and making the transformation u is equal to t square there, and write and compare with the forms of the densities. However, one can look at an easy representation. See, we can write t as x divided by root y by n, where x is a standard normal and y is a chi square variable. So, if I look at t square, that is x square by y by n. Now, this x square will be chi square on 1 degrees of freedom and y will be chi square on n degrees of freedom. So, this is nothing but the definition of an f variable on 1 and n degrees of freedom. Sampling distributions are extremely useful in statistical inference and they are used all the time. I will give a couple of applications here. Assume that the time to failure of a bulb is a random variable with say mean mu and standard deviation say 100 hours. If failure times of n bulbs are to be recorded, how large n must be so that the probability of the average of those observed differs from mu by less than 50 hours is at least 0.95. That means, how much should be my sample size such that the sample average and the population mean should differ by less than 50% and this probability should be at least 0.95. So, we can make use of the central limit theorem here, because the only information about the distribution that we are having is that it is a particular distribution with certain mean and certain variance. So, the conditions for application of the central limit theorem are valid here. So, we will have root n x bar minus mu by sigma, that is 100. This will be approximately normal 0 1 as n becomes large. So, by this statement we have the condition here that probability of modulus x bar minus mu less than or equal to 50. We want to put this to be greater than or equal to 0.95. So, we approximate this probability by converting to, by making use of the central limit theorem. So, this is less than or equal to 50 root n by 100. So, this is approximately a standard normal random variable, then this probability is, I can replace this variable by z, where z is a standard normal variable. So, this can be written in terms of the CDF, that is twice phi root n by 2 minus 1 greater than or equal to 0.95. So, I have made use of the central limit theorem here, and this gives us phi of root n by 2 greater than or equal to 0.975. So, from the tables of the normal distribution, root n by 2 must be greater than or equal to 1.96 or n must be greater than or equal to 16. So, we need minimum sample size 16, so that the sample average and the population average do not differ by more than 50 and the probability of that should be at least 0.95. Let me give one more problem here. So, we consider independent random samples of size 5 from two normal populations and they have the same variance. So, what is the probability that the ratio of the larger to the smaller variance exceeds 3? So, this problem is important in the following sense. See, we have taken two samples from the same population. Now, we want to check whether there is too much variability in the sampling process. So, we look at the variances of the two samples, and one of them will be naturally larger and one will be smaller. So, we are saying that the ratio of the larger to the smaller exceeds 3. What is the probability of this event? So, if we write in terms of S1 square and S2 square, basically we are requiring here what is the probability that S1 square by S2 square is either greater than 3 or S1 square by S2 square is less than 1 by 3. What is the probability of this? Now, if we have taken the samples of size 5 each, then by the formula that n minus 1 by m minus 1 S1 square by this one, we get that S1 square by S2 square follows F distribution on 4 and 4 degrees of freedom. That means, for calculation of this we have to look at the either the tables of F44 or we write down the density of F44 here. Fortunately, the density of F44 becomes a quite simple form. So, we can write this as 1 minus probability 1 by 3 less than or equal to S1 square by S2 square less than or equal to 3, and this turns out to be 1 minus 1 by 3 to 3, and the density function of F4 is 6 x divided by 1 plus x to the power 4. So, this integration can be done easily and the value turns out to be 0.3125. So, various problems which relate to the sample means or the sample variances or the comparison of the means or comparisons of the variances can be solved using sampling distributions. In the portion of point estimation, confidence interval estimation and testing of hypothesis, we will have frequent uses of these sampling distributions. So, in particular we have considered normal distribution itself as a sampling distribution, because for the large samples any sample mean will be approximately normally distributed under certain condition of course. And then when we are sampling from normal distributions, then certain functions which are related to the means and the variances, they are having chi-square, t and f distribution. So, these are in particular 4 important sampling distributions. There are many more sampling distributions, but they are not as frequently used in practice.